Hello everyone, and welcome to lesson 20 on the Save My STEM Physics channel. It's been a little bit of time since I recorded one of these videos, but I should be back on it now. And this is another installment in the wave interactions part of Year 12 Physics. And it's a little bit of a long one, so buckle in, and hopefully you'll understand it all by the end of this. So, um, as I said, it's coherence, double slits, and God, coherence, double slits, and diffraction, double slit and single slit. Um, so let's just get straight into it. Coherence is um, the property of two waves um, comparative to one another where they have a constant phase difference. So you may recall from a previous video, we've discussed phase difference being um, 2 pi multiplied by the horizontal distance between 2 points on different waves over the wavelength of the wave. And that is what phase difference is. And so for something to be coherent, it must have a constant phase difference, which implies two other properties of the waves, which is that they have the same frequency and wavelength, given that they are both electromagnetic waves, so they will ultimately have the same wave speed anyway. Coherence can come from multiple sources. So if an exam asks you um, to note down what what source you could get coherence from, um, you can say a laser. You can say uh, any source of light passing through a double slit. And yeah, so that's what coherence is, and those are coherent waves. But why is that important? It's because when we work with these concepts, which are diffraction, single slit diffraction, double slit diffraction, and interference, they most notably must happen between coherent waves, or at least in the A-level specification, that's how they work. That we don't work with anything that isn't coherent. So what actually is diffraction? Diffraction, the definition that you need to know, if I just write it down very quickly, is that when a wave spreads out after passing through a slit or along a boundary. So that's the definition for diffraction, and you'll see it mostly in the case of slits rather than boundaries. But basically, if I have a wave source, a wave coming into a slit here, it sort of acts as its own wavefront and interferes with itself, causing it to have multiple wavefronts, multiple places of maximum amplitude, and causing it to cancel out in some places, which can be detected on a screen further back. And this is actually a case of single slit diffraction, which is one of the things that we need to get onto. So now that we have an idea of what diffraction is, we need to look into a little bit more of the specifics or the maths behind it or things that you have to recall about it. So one of the big things that you have to know is the smaller the slit, so if the slit is here, the smaller the slit, the more diffraction, so the more it spreads out, is the basis of it. But the slit can't be so small that the wave physically cannot get through. So a way to write that is slit width must be bigger than lambda, must be bigger than the wavelength of the wave, but we want it to be close to lambda. Um, so if this is 1 nanometer, then we'll probably want this to be about 10 10 nanometers or something along those lines. That would probably be very difficult to make, but that's a very idealistic sense of the slit width that we'd like. Um, Another thing that you want is the distance from the slit to the screen. So this distance here, which I'm marking big D, you want that distance there to be many magnitudes larger than the wavelength. So you want that to be 1,000,000 times larger than the wavelength. Um, just many magnitudes, so many orders of 10. So yeah, that's general basis of it, because that's how you get good results or results that actually work. And because the formulas that we use when we talk about diffraction are roughly approximate, um, this fits mathematically the best because the approximations that we make aren't that far off anymore because things are so big. Um, and yeah, so that's some of the basis of single slit diffraction. These rules follow into double slit diffraction, but let's stay on the topic of single slits at the moment, and let's have a look at what we call their diffraction pattern or interference pattern. And if it's with monochromatic light, so light of one color coming through to the slit, then on the screen we will get something looking like this. Now that's not a very great drawing, I have just done it very quickly, but let's ignore that line there. We have what are called maxima, so that's a maximum amount of light. That's where the light is constructively interfering with all its many wavefronts coming out from the diffraction. And we get light there, we get light there. Everywhere else in between it's dark, and we get what's called a central maxima, which is double the width. I know it's not particularly great drawing there, to be honest, but this width here should be double the width of any of these other ones, which do look roughly the same. And yeah, so that's a single slit diffraction pattern, double width in the middle, same width everywhere else. If it is colored, if it's white light, then it will be a white center. It looks roughly the same. White center with red edges on either side, and then the outer maxima will have violet insides and red outsides. And that's the same on this side, so it'll be violet over on this side, red over on this side. And that's because each wavelength diffracts by a different amount, which is described better with double slits because we have a better approximate formula for that, which I'll show you in a second. So let's move on to double slits. Double slits is when if you have something like this, where the light goes through both, and again it forms its own wavefront, interfering with itself, causing places of maximum and minimum due to constructive interference. And the wave pattern that we'll get on a screen over here, which is a distance big D away, is very similar to that of single slit diffraction, except there's no double width central maxima. Every maxima is the same width. But another thing we must transition from is with double slits, we no longer call them maxima. We call them fringes. Not a clue why, but we do. So these fringes are equally spaced. They all have the same width. And this is described by an equation. W equals lambda d over s. So what do all these letters mean? W is the fringe spacing. So the space from the middle of one to the middle of the other. Alternatively, you could do the left-hand side of one to the left-hand side of the other, or the right-hand side to the right-hand side. But it can't be. Do you know what I mean? It can't be right to right. Sorry, it can't be right to left or anything like that because that would be inconsistent. So fringe spacing. We then have lambda, which you already know, wavelength. D is the distance to the screen, and S is the slit separation, not the number of slits or the width of the slits, it's the slit separation. So if it tells me that I have 10, sorry, if I have 1,000 slits per meter, that doesn't tell me the distance between the slits. What I have to do is I have to do 1 over 1,000 to find the slit separation. Alternatively, another thing that it could tell you is it could tell you uh, 1,000,000 slits. Oh, no, sorry, 1 slit per millimeter. And in that case, you'll have to do 1 times 10 to the minus 3, because that's the unit conversion from millimeters to meters, over the amount of slits per that length, which is 1, and that will get us the exact same result of 0.001. So that's W equals lambda D over S. That's double slit diffraction. And yeah, that's, I believe, all for Young's double slits. That's the diffraction patterns that you have to know. Again, the same thing happens with white light. So white light here will be a white maxima, a white fringe, sorry, in the middle, with red outsides and violet insides on the outer maxima, not on the central maxima. This also describes why the red is on the inside of the central one, and then it becomes violet, red, because red has the longest wavelength, so that means its fringe spacing is going to be higher, and that's why it's out more. So yeah, that's all for this lesson. That's coherence, double slits, and diffraction. We do have another lesson on a very similar thing called diffraction gratings, which will be coming up very shortly. And yeah, so thank you very much for watching. Hope this has helped you understand, and I'll see you on the next one. Bye.